We're going to start on chapter 24 now. This is, of course, the oceans and the atmosphere and their combined effect on the climate. All right, so one thing I should say right off the bat is that we're going to think of the atmosphere as a fluid. The ocean, obviously, people already think of the ocean as a fluid, but the way air moves can also be thought of as fluid motion. I mean, I know most people don't really think of it that way, but it really is. All right, so especially when we talk about pressure and stuff like that. These are the different topics we're going to cover. Is just the general the Earth's atmospheres and oceans. The components of the oceans, how waves are created, how tides are created, and we'll talk about the how the shorelines are shaped, the components of the Earth's atmosphere, how solar energy gets to the Earth, and then what happens to that solar energy, and then the driving force of air motion. And then what we'll see is the global circulation patterns with both the oceans and of course the atmosphere. All right, so let's get into this. All right, so the first part is to just notice the simple fact that the Earth is 71% ocean. It's mostly ocean, right? Only 29% of the mass of the Earth, or the surface of the Earth, I should say, is land, right? And that's something to be considered when you think about where humans can live, where animals and plants and stuff like that can live. All right, so the thing that's really important here is there's a big difference, and hopefully, if you haven't had the lab on, where we took four beakers, a beaker of soil, a beaker of sand, a beaker of rocks, and a beaker of water, and we put them under a lamp, which just represents the solar energy coming to those different materials, and one of the things that hopefully you noticed in that lab, if you've already done it, if not, you're going to do it really soon, is that the water took the longest, or it should have anyway, in the lab. The water took the longest for the temperature to rise. All right, so of all the other things, the soil, the rocks, and the sand. All right, and so what that means is that water has this quality that we call the heat capacity. So it takes water a long time to warm up, right? Because it has such a high heat capacity, and by the same token, once water is warm, it takes a long time for that water to cool down. And in fact, the water will carry the heat from location to location, as it does with the Gulf streams, for example. All right. And before I get to that, let's. So one of the things that I want to point out is which you can't quite see it here, but this is right here is the western coast of the United States. There's Mexico. There's the Baja Peninsula. But if you look at the United States, the latitude of where San Francisco is, for example, and where Wichita, Kansas is, they're roughly the same latitude, right? But Wichita, Kansas, and San Francisco have vastly different climates. The climate in San Francisco, because San Francisco is right on the ocean, the ocean, the fact that there's this huge body of water, it causes San Francisco to have really small fluctuations over the course of a year between really high temperatures and really low temperatures. Whereas opposed to, I know this isn't in Kansas, obviously it's on the other side, but, if you think about Kansas, right, in the middle of the land, of the mass of northern North America, not near any kind of water or anything like that, Kansas has great variation in temperature, right? So between winter and summer, whereas winter and summer for San Francisco they're relatively there's of course differences, but not as great a differences. All right, so that's one of the things that the water does. And another thing, of course, is something that happens. And so later, let's see. Here is England right here, and Norway, and so right near the equator, on the near South America, the Gulf Stream rises. It hugs the part of the United States, and it's like 200 miles off the shore of Florida in different places, and then it crosses the Atlantic. And what happens is that Gulf Stream has this hot water. Even though you're in these northern latitudes, when you get to England, it keeps England at a warmer than normal winter. Like, I shouldn't say normal, because it's normal for them. But if there wasn't a Gulf Stream, for example, the winters in England and in Norway would be much greater. They'd have much greater variation in temperature. All right, so that warm water that's always coming from the equator, and crossing the Atlantic in the form of the Gulf Stream, that keeps these locations and other parts of Europe as well, in relatively, it affects the changes, the seasonal changes in temperature, right? So in other words, the seasonal changes are not as great because of the Gulf Stream. All right, so there's two examples. All right, so now we'll talk about the atmosphere for a little bit. So the Earth, we think, had a very primitive atmosphere right after it was formed, and actually during the formation of the Earth. So this would have been, if you refer to the last chapter, the Hadean period, right? So this was also known as the late heavy bombardment, where lots of asteroids and comets and meteors were hitting the Earth. During that time, the atmosphere of the Earth would have been composed of the original matter that made up the solar system, hydrogen and helium. Okay, so that there would have been an atmosphere of hydrogen and helium. This is as the Earth was forming, so even before the Hadean period. And then when the sun, we'll talk a lot more about this when we get to the chapters on astronomy. When the sun turns on, basically what happens is the sun begins to fuse hydrogen into helium. That's how all the stars work, by the way. Hydrogen is turned into helium, and during that process, it releases energy, as do all the stars, right? That's how the stars generate their energy. Anyhow, when that happens, there are particles, sometimes charged particles that come from the sun, and basically this is called the solar wind. The solar wind would blow away any hydrogen and helium atmosphere that the Earth would have. And by the way, and the other thing is, when the Earth fully forms, it has enough mass, so that the gravitation of the Earth is not enough to hold on to the hydrogen and helium. That these atoms are just too light to stay in the atmosphere for very long. I mean, they'll stay there for a while, but over the course of millions of years, that they'll eventually leak out into space. All right, so in the next atmosphere, what we consider really the atmosphere, the very early atmosphere of the Earth, comes from volcanoes, and the stuff that's coming out of volcanoes is primarily water vapor. All right, so there's lots and lots of water vapor coming out of volcanoes, and carbon dioxide. All right, so those, and there's other gases as well. There's sulfur, and there's chlorine and things like that coming out of the volcanoes. All right, but the primary things are water vapor, and then to a much less extent, carbon dioxide is coming out. And so that was the original atmosphere, is just water and carbon dioxide for the most part. I mean, there are small traces of other things as well. And then during the Archean period, remember so this is deep into remember in the last chapter we talked about the Precambrian period. During that time, this primitive form of life, this cyanobacteria, also known as the blue-green algae, began photosynthesizing. Most of the free oxygen, went into the oceans, dissolved into the oceans, but then eventually enough of it gets put into the atmosphere, and the atmosphere begins to have O2 molecules, the free oxygen, the stuff that we need now to breathe. The animals need to breathe. All right. Higher in the atmosphere, that those as those O2 molecules accumulated higher in the atmosphere, they undergo a chemical reaction and become O3 molecules. And O3 molecules high up in the atmosphere, and in fact they are up in the stratosphere. Well, they're actually between the stratosphere and the mesosphere. But anyhow, the O3 molecules begin to accumulate, and that has this profound effect on life on the Earth, because the ozone is a filter for ultraviolet light, and so ultraviolet light, which is very, very damaging to life forms, the fact that the ozone begins to filter it allows life to evolve in all sorts of different ways. And then, of course, all that water that was coming from the volcanoes begins to condense, and of course you have rain and snow forming, in the land, and then of course you're forming very primitive oceans. Now, one thing that's really important to understand, and we've been studying this for a long time. We'll talk a little bit more about it when we get to astronomy, but if you add up all the water in all the oceans, there's not enough. There's not enough volcanic activity since the creation of the Earth 4.5 billion years ago to account for all that water. So the water must have come from extraterrestrial sources, and we believe, of course, it did. It came from extraterrestrial just means off of the Earth. I'm not talking about aliens or anything like that. But it came from comets, which are really just giant dirty snowballs, and asteroids. Asteroids contain tremendous amounts of water as well. And as those things crashed into the Earth during the late heavy bombardment, the Hayden period, that would deposited tremendous amounts of water, on the Earth, right? And of course, there's a lot of water that's trapped in the rocks on Earth. Like, the water that we think of is the water in the oceans or in rivers and so forth. But there's tons and tons of water that's trapped in rock formation, in actual, the formation of actual rocks. All right, so now we'll look at the ocean.